Good morning. So, we are learning discrete mathematics subject, and in unit 4 we have been discussing algebraic structures, semi-groups, groups, monoids, group codes, homomorphism, isomorphism. So today we will revisit these two topics, homomorphism and isomorphism, with the help of one or two problems. Okay. So the first keyword we are referring is group homomorphism. So this is a set G comma star, where star is the binary operation to be performed. There is one more set G dash with this binary operation to be performed. So there are two sets here, and we have to establish a homomorphism, group homomorphism among these two sets. Let us say there is a function mapping from G to G dash such that f of a star b, f of a star b indicates what? Okay, a and b belongs to G, and there is an operation called as a binary operation being performed. The resultant of that will be f of a, the binary operation being performed on G dash, f of b. So here if it is an addition, on the left side there will be addition. Here on the right side, let us say for this other set G dash, the operation is, let us say, multiplication. So here the resultant will be multiplication. So this will establish homomorphism among two sets. Now to prove that isomorphism also property also is there, first we need to prove that homomorphism is there. After proving homomorphism, how do we prove homomorphism? Like this: f of a binary operation b is equal to f of a binary operation b. Here the binary operation is related to, say, this set, and this binary operation is related to, say, this set. After that, once homomorphism is proved, we have to prove bijection relation. Okay. So which function will be a bijection function? It will be having two properties. One property is one-to-one property, and the another property is onto property. What is one-to-one property called as injective property? What is onto property called as surjective property? What is the meaning of one-to-one property? Let us say there is a element A. Okay. So for that element A in say one set, there is a distinct element B in some other set. So this is one to one. Same here, what is the meaning of onto? The meaning of onto is, let us, B is an element in set number 2. So B will be mapped to at least one A in set number 1, let us say. This is also rephrased as, for every B there is a pre-image in A. So this property is surjective onto, this property is injective one-to-one. If one-to-one and onto are proved, then it indicates that bijective. So if bijective is proved, then it indicates that group isomorphism. And for group isomorphism, we will be using this symbol. Okay, this 3 lines. What it indicates here? G, these 3 lines, G dash means these two sets are having the property of isomorphism. Let us take an example. We have one set where the set consists of real numbers, and the operation being performed is a addition operation. So the binary operation here is an addition operation. Then we have another set, okay, R plus. So R plus, what will it will indicate? A set of positive real integers, positive real numbers. This will be only real numbers. What operation we are saying here? Here we will take it as not a binary operation but a multiplication operation. So what we have to prove? We have to prove homomorphism and isomorphism among these two. Homomorphism and isomorphism among these two. What is the mapping? R maps to R plus. Under what condition? F of x is equal to 2 to the power of x. F of x is equal to 2 to the power of x. Whenever we have to prove homomorphism and isomorphism, first we have to prove homomorphism. For proving homomorphism, remember this functionality. F a star b is equal to f a, the binary operation f b. This binary operation is related to this set, this binary operation is related to this set. So, what we have done is, we have taken two elements a comma b belonging to this set R, real numbers. So, a and b are real numbers. So, what operation is here? The operation being performed is plus. So, a plus b. So, a plus b, f of a plus b. So, this is f of x is replaced with f of a plus b. So, 2 to the power of x will be replaced with again a plus b. So, it will be 2 to the power of a plus b. How I can represent 2 to the power of a plus b? 2 to the power of a plus b can be represented 2 to the power of a multiplied by 2 to the power of b. So, 2 to the power of a can be as f of x is equal to 2 to the power of x, f of a will be equal to 2 to the power of a, f of b will be equal to 2 to the power of b. So, replacing 2 to the power of a with f of a, 2 to the power of b with f of b. So, f of a star f of b. So, on the left side, f of a, whatever the binary operation of the first, that is plus b, and on the right side, f of a, whatever the binary operation on the right next set, that is multiplication. So, this proves homomorphism. Once homomorphism is proved, what we need to prove? We need to prove isomorphism. For isomorphism, what we have to prove? Bijection. For bijection, what we have to prove? 1 to 1 and on to 1 to 1. So, for 1 to 1, we can say that 2 to the power of a is equal to 2 to the power of b, as f of a is equal to f of b. F of a is equal to f of b. So, naturally a will be equal to b. So, as a is equal to b, 1 to 1 relationship is maintained. What is the meaning of 1 to 1 relationship? For every a, there is a distinct b. Okay. Second thing to be proved is onto. For onto, what is to be there? Each b is mapped to at least one a. For that, so for onto, actually what you have to do is codomain. So, you have domain and codomain. Codomain you can take it as second set. So, it will be equal to range. Okay. So, for example, there is a y set, there is an x set. So, y of, there is an element say y belonging to y set. So, there exists x belonging to x. So that f of x is equal to y. This has to be proved. So, in our case, what is f of x? In our case, f of x is 2 to the power of x. So, we are taking one more element called as c, which belongs to R plus, and R plus is a second set, right? R plus is a second set, which is a set of real numbers, positive real numbers, set of real positive numbers. Now, this will be equal to 2 to the power of x. Am I right? So, as f of x is equal to 2 to the power of x, and as c belongs to R plus, so c will also be equal to 2 to the power of x. So, x will be equal to log 2 of c. So, what will be f of x then? F of x will be 2 to the power of, replace x with log 2 of c. So, 2 to the power of log 2 of c. So, again I am replacing this x with log 2 of c. So, f of log 2 of c will be equal to 2 to the power of log 2 of c, which will be equal to c. This has to be proved. So, hence this is onto, hence this is bijection, hence this is isomorphism. So, let us take one more example. This is one set, this is another set. The binary operation here is plus, the binary operation here is multiplication. This is real numbers, this is real positive numbers. The mapping is R positive maps to R, and what is the definition? F of x will be equal to log 10 of x. Okay. Again, what we have to prove? Isomorphism. For proving isomorphism, what is to be proved? Homomorphism. So, same, take two elements a comma b belonging to R plus now, because as the mapping is from R plus to R. So, what is the operation being performed here? Multiplication. So, f of a star b equal to, what is there? Log 10 of x. X will be replaced with what now? A star b. So log 10 of A star B. So how do I write it? Log 10 of A plus log 10 of B, which is equal to f of A plus f of B. So this relationship indicates homomorphism. After homomorphism, what is to be proved? Isomorphism. For isomorphism, what is to be done? Bijection. For bijection, what is to be proved? One-to-one relationship and onto. So let f of A equal to f of B. So naturally, when I say that, log 10 of A will be equal to log 10 of B. Remember here. So that indicates what? A equal to B. That indicates what? F is 1 to 1. Okay. So same thing what you have to do is you have to prove onto relationship also, just as you proved onto here. How you proved onto here, same thing you take and try to derive that. So let us again just have a relook at what isomorphism says. Okay, isomorphism is between two sets. But for isomorphism to be written, homomorphism is to be proved. And for homomorphism to be proved, this has to be proved. Okay, you have x and y, say here, of one set. Then you have to separate it, and whatever the operation being performed for x and y separately, you have to take it. After that, one-to-one and on-to relationship is to be maintained. Say for example here, A is an algebraic system with star as a binary operation. B is an algebraic system with this star as a binary operation. So we have taken this composition table for the elements A, B, C, D, some operation being performed. But what operation here? The binary operation is star. Now what we are doing is, from this we are deriving this. How? By changing the name. So this star is replaced with this star. A, B, C, D are replaced with alpha, beta, gamma, delta. So by changing names and operations, here what happens is these two systems, these two algebraic systems are isomorphic. For example, B comma star is isomorphic to A comma star. If there is a one-to-one function from A to B, okay, like this, f A star A1 star A2 is equal to f A1 star f A2. Here actually it should be another star. So f of A will be equal to alpha, f of B equal to beta, f of C equal to gamma, f of D equal to delta. If this is written, it is isomorphism. So g of A equal to delta, g of B equal to gamma, g of C equal to beta, g of D equal to alpha, that indicates image is being retained. So thank you.